Oxford, who's going to tell us about string theory amplitudes on ADS.
Thank you very much. So first, I would like to start by thanking the organizers for putting up this lovely conference and for giving me the opportunity to present our work here. So I will be giving a string theory talk in Eurostrings. I thought it's quite appropriate. And I will be talking about a set of tools to compute string theory amplitudes on curved backgrounds, and in particular on anti-de Sitter. Now we can ask why we are interested in scattering amplitudes. Of course, as physicists, they should interest us because they are the objects, the observables, that allow us to test the predictions of our theory. But even in a more abstract way, they can teach us a lot about the structures and symmetries of our theory. And things that are not at all clear from the Lagrangian, they may be clear from scattering amplitudes. And in particular, there has been a huge amount of progress regarding amplitudes in flat space, and it is interesting to understand how much we can say about ADS. Today, more specifically, we will deal with a very specific example, which is the scattering of 4 massless strings for gravitons on ADS 5x5. And just to have it, to give this like a review, we will start by reviewing the story in flat space, okay? And please stop me if you have questions. Now, a scattering amplitude, in this case the 4-point scattering amplitude, is basically the probability that 2 particles, or strings, colliding with momenta P1 and P2, result into 2 other particles with momenta P3 and P4. The amplitude can depend on many things. It depends on the parameters of your theory, here collectively denoted by G. It depends on the particles you are scattering, their masses, polarizations, etc., and also on the momenta of the particles being scattered through the 3 Mandelstam invariants S, T, and U. For the 4-point graviton amplitude in flat space, the parameters of your theory are these 2, the string coupling constant GS, which measures the probability that 2 strings come into 1, or 1 string splits, and the size of the strings, which is square root of alpha prime. In addition, the amplitude also depends on the momenta pi and polarizations epsilon I of the 4 external gravitons. Now, it turns out that supersymmetry fixes fully the dependence on the polarization of these gravitons through a simple computable prefactor, and we will focus on this non-trivial beast, which is a function of GS, alpha prime, and ST and U, the 3 Mandelstam invariants, okay? Now, this is still a very complicated object, so we can do a genus expansion, and actually, in a very natural way, the string theory computation organizes into a genus expansion, where the first contribution is the genus 0 or 3-level contribution, then we have genus 1, genus 2, etc. Now, it is a textbook computation. You can find it in Green, Schwarz, Witten, for instance. The fact that in flat space, we can use worldsheet theory in principle to compute all of these. So for the genus 0 contribution, we get this beautiful integral over the complex plane. But note already that the genus 1, the expressions are super complicated, okay? But in this talk, we will be talking only about genus 0 amplitudes. These are hard enough. And for genus 0 in flat space, we get this beautiful integral over the complex plane, okay? Now, this is something that you can do in Mathematica. It's very cool. Set is equal to x plus iy, set bar x minus iy. You plug this and do the computation. To young people, I propose, so I encourage to do that. And you get the following result, okay? This result is a very, very famous result. is called the Virasoro-Shapiro amplitude, and is this beautiful function of the three Mandelstam invariants S, T, and U. It's this symmetric function of alpha prime, S, T, and U. Now, this answer, this amplitude, is probably the most famous result of string theory, has a lot of properties that we will review now. Many of these properties are very well-known properties. And one property is less appreciated, and we will put special attention on that less appreciated property, okay? All these are things that you can explicitly check from this answer. The first is that it is crossing symmetric in S, T, and U. Here, S plus T plus U is equal to 0 because we are scattering gravitons. Second is that this amplitude has poles due to the exchange of particles, and here you can see that the poles always happen whenever alpha prime S is equal to an integer, to a natural number, also 0. And in our conventions, these are poles due to the mass of particles, of this mass and spin L. With these residues, some polynomials of degree L. In addition, it has some Regge behavior. So for large T, finite S, the amplitude behaves according to this formula. This is also a famous formula of string theory. And also something that you can do, series expansion with Mathematica, is an alpha prime expansion. Now, remember that I told you that alpha prime is the size of the strings, so that when alpha prime goes to 0, you get the supergravity result, 1 over STU, and then, in addition, you have a tower of string theory corrections, which is zeta 3, zeta 5, and so on, okay? And here, we have always a polynomial, of degree 0, degree 2, and so on in the variables S, T, and U, okay, by dimensional analysis. Now, any questions at this point? So these are the properties of the Virasoro-Shapiro amplitude. What is beautiful, actually, and we will go back to that later, is that Virasoro didn't have this answer. The only thing Virasoro had was the list of properties, and he was able to guess the answer. We will try to play a similar game later on. Now, a less appreciated property is that if you look at this alpha prime expansion, you notice that we have zeta 3, zeta 5, next you have zeta 3 squared, etc. And to all orders in alpha prime, we only get odd zeta values. Zeta 3, zeta 5, zeta 7, never the even ones, okay? And actually there is a beautiful representation of the Virasoro-Shapiro amplitude, which is given by this exponential, and in this representation it's fully clear that only odd zeta values appear, okay? Now, this seems to be quite innocent, is like an innocent formula, but it is quite deep from a mathematical point of view. And in the next 5 minutes, I will tell you why this is quite deep from a mathematical point of view. Is that okay? Perfect. So, zeta values, let's talk about maths for a little bit and then go back to physics. These zeta values, or multiple zeta values in general, can be defined in terms of sums, and this is the Wikipedia definition of zeta n, but also they can be defined in terms of polylogarithms evaluated at z equals 1. When we define the nth polylogarithm of z equals to this, and you see that if you plug z equals 1, you go back to this definition here. So if you evaluate this polylogarithm at z equals 1, you get the zeta value Zn, okay? Now, while these series converge only inside the unit disk, we know very well that polylogarithms can be analytically continued to the whole complex plane. And for instance, L1 set defined like this is just the minus logarithm of 1 minus set. And by this integral representation, you can extend this, you can analytically continue them to the whole complex plane. Of course, the price that you have to pay is that these logarithms are not single valued, okay? And as we know, these the usual logarithms have a branch cut from 0 to minus infinity, and this is a problem, okay? Now, we physicists don't care so much about this, but it turns out that mathematicians hate functions which are not single valued, okay? And they work hard, and they could prove that actually one can define what is called single-valued polylogarithms. And it turns out that there is a unique map which takes these multi-valued polylogs to single-valued polylogarithms. And the map is unique provided you put some conditions, and these single-valued polylogarithms, they are now functions of set and set bar. They are weight-preserving linear combinations of Lie omega set and the Lie of set bar, and they are such that the differential relations are preserved. So for instance, you see from here that if you take derivative of this with respect to set, you get 1 over set Lie n minus 1 of set. We require the same for these single-valued polylogs. So from these multi-valued polylogarithms, which are holomorphic, just functions of set, but they are single-valued, multi-valued, sorry, we define the single-valued ones, which are now a function of set and set bar. Okay? So for instance, if you do this map for log set, you get log set plus log set bar, which is very cool and completely single-valued if you go around the complex plane, and you can do the same for Lie2, Lie3, etc., etc. Is that okay? Beautiful. But now, we can do something quite smart, okay? Remember that I told you that if you take a polylogarithm and evaluate it at set equals 1, you get a zeta value, okay? Now, what we can do is we take a single-valued polylogarithm and evaluate that at 1. Okay? Now the single-valued one. Single-valued polylogarithms evaluated at set equals 1 define what we call single-valued zeta values. Okay? So, for instance, if you take this combination, this combination here, and you set equals 1, so you try to define a single-valued version of zeta 2, you actually get 0. But if you try to define a single-valued version of zeta 3, you get twice zeta 3. Okay? And more generally, if you try to define a single-valued version of the even ones, you always get 0. But if you define a single-valued one of the odd ones, you get twice the usual zeta values. Now notice that you shouldn't think, so a zeta function, a zeta value, sorry, is a number, right? And I am telling you, some numbers are single-valued and some numbers are not. So most people in this room would just start vomiting if I tell something like this, right? What mathematicians mean by that is that one arises from a single-valued function once you set equals 1. And the others do not. Okay? So zeta 2, you cannot get like that. Zeta 3, you can. Okay? You can get it by evaluating this L3 at 1. So, odd zeta values are single-valued, while the even ones are not. And in general, what happens is that single-valued zetas are a subset of the usual zetas. Okay? So we have all the zeta values. The odd ones are good, single valued. The even ones are not. So the message, the important message, now in a mathematical way, is that the alpha prime expansion of the Virasoro-Shapiro amplitude contains only single-valued zetas. Okay? So that is the message that I would want to give to you. Is that okay? So, beautiful. Are there any questions at this point? Yes?
You, like, to analytically continue the zeta function, you need to introduce this polylogarithm. But
Yes.
there could be another function which could have defined which could reduce to some values to the even zeta value.
Absolutely. So the point, very good, excellent point. So the point is that this map is unique, okay? So mathematicians, indeed, you are completely right, of course, and if this map wasn't unique, for instance, let me give you an example. Imagine that you take this L2, defined as it is, and you put plus zeta 2 here, right? This could be single valued as well. And if you evaluate it at 1, you would also, you will get zeta 2, right? But the point is that mathematicians give a list of conditions, and in particular, I didn't write it because I didn't want to be too technical, but this vanishes as you take z bar to 0. And with this list of conditions, this map is unique. So the map is unique, and because of that, this is a very well-defined construction, okay? And of course, what I am showing you here doesn't seem so cool, because I am just talking about the usual zeta values. But the point is that there are some more complicated zetas, for instance, 3, 3, 5, right? And then I will put something a bit random, zeta 11, and then zeta A3, right? And what the mathematicians have proven is that the three of them don't arise from a single valued polylogarithms, but only this specific combination, let's say, plus 2 times this, minus 3 times this. And then, when you go to more complicated string theory computations, closed string theory computations, the precise combination that appears is always this combination and not the other combinations. And that's why mathematicians are very excited. Now, of course, this is a bit technical, and I am just giving you the example with the usual zetas with only one index. But this is quite impressive, right? And the more deeper you go into these levels, the more and more impressive it becomes. Does this answer the question? Beautiful. Very nice. So now we would like to, beautiful, so we know all there is to know for now about string amplitudes in flat space. Now we would like to try to compute some string theory amplitudes on curved backgrounds, and in particular on ADS 5×5. Now, in this case, we don't have a worksheet description. We have Ramon fluxes, but it turns out that for the special case of ADS 5×5, we can make a lot of progress thanks to a lot of indirect tools that we are about to use, okay? And now, in the second part of this review, we will see how all these can help us to construct these amplitudes in ADS. The first tool, sorry, is the ADS CFT correspondence, okay? The ADS CFT correspondence tells us how we should think about string amplitudes on ADS. And it tells us in particular that a string amplitude on ADS, our working definition, will be the correlator of a local operator in the conformal field theory at the boundary. And in particular, in this case, we are dealing with a 4-point amplitude, so that on the right-hand side, we have a 4-point correlator that we need to consider. Okay? I don't know if you have seen ADS CFT already in the school. You have, but let's define it more properly. Now, In particular, we will look at the original version, where string theory on ADS 5 cross S5 is dual to 4-dimensional n equals 4 super Yang-Mills. The duality also provides us with a dictionary between the parameters on both sides. On the left, we have the string coupling constant GS and the common radius of ADS and S5. And on the right-hand side, we have the Yang-Mill coupling constant, G Yang-Mills, and N from the gauge group SUN. And the dictionary tells us that GS is basically 1 over N, and the radius are squared in units of alpha prime, maps to the Toff coupling square root of lambda, which is this combination here. So by looking at this, you can see, for instance, that the genus expansion on the side of the string amplitude, that was an expansion for a small GS, is the maps to a 1 over n expansion in terms of the correlator on the right. While stringy corrections to supergravity map to 1 over lambda corrections on the right. And finally, what we want to scatter are gravitons on ADS. And in ADS CFT duality, you map the graviton to the stress tensor. So in n equals 4 super Yang-Mills, because it's supersymmetric, we consider a scalar operator of dimension 2, which is in the stress tensor multiplet. It's the highest weight, the lowest weight operator of the stress tensor multiplet, okay? So what we want to do, we want to consider 4 of these scalar operators of dimension 2, and we want to compute this in a 1 over n expansion. Or we want to consider this in a 1 over n expansion. Is that okay? Very nice. So, n equals 4 super Yang-Mills. So this, we will consider this gauge theory with gauge group SUN. All the fields are in the adjoint representation. This has the maximal amount of supersymmetry and also has conformal symmetry. The symmetry group is called PSU 2,2/4. It's just a name. I could have put Roberto or whatever. And it turns out that the bosonic part of this is SO 2,4, which is the conformal symmetry group in 4 dimensions, and the R symmetry group for n equals 4 in 4 dimensions, which is SO6. The operators we will consider for this talk, there are 2 kinds of operators which will be relevant. One is this very simple operator. So the theory has these scalar fields, phi I, and you just take trace of phi I, phi j. This I is in the fundamental of SO6, so it goes from 1 to 6, so that this operator is in the symmetric traceless SO6, of rank 2 of SO6. It's just trace of phi I, phi j. And this operator is an extremely simple operator. It's the simplest protected half BPS operator of the theory, and the dimension is always 2. Okay? So this is the operator whose 4-point function we will consider. N equals 4 super Yang-Mills is not that boring, and there are other kind of operators, and another famous operator is the Konishi operator. And for the Konishi operator, we contract these 2 indices so that it is in the singlet of SO6. And then this is basically the Konishi operator. And the Konishi operator has dimension 2 at weak coupling, and as lambda increases, it has a dimension that grows with lambda to the 1/4. Okay? So this arises from this famous work by Gabser, Klebanov, and Polyakov. So this goes to 2 lambda to the 1/4 at the strong coupling. Okay? And these plots are from these beautiful results of integrability that we have seen over the last 20 years. Beautiful. So what we are going to do now, we are going to take 4 of these guys here, and we are going to consider the 4-point correlator of these 4 protected operators in n equals 4. Okay? Now, it turns out that very much like what happened in the scattering of gravitons in flat space, this is fixed by symmetries up to a function of two cross ratios. And basically, this correlator is equal to a prefactor times a function of u and v, where u and v are these two conformal cross ratios, which I define here. Okay? So this is the non-trivial part, and this is the part that we will focus on. Is that okay? So the claim is that this has a lot of indices, but supersymmetry is very powerful, and at the end of the day, we end up with just a function of two variables. Very much like in the scattering of gravitons, you had a function of three variables, st and u, with one constraint. So it's very much the same. Is that okay? Beautiful. Now, this function, this 4-point correlator, of course, is still a function of the parameters of your theory, which are n and lambda, and is supposedly a highly non-trivial function of n and lambda. Okay? We are not powerful enough to compute this, so what we start doing is we consider the leading non-trivial term in a 1 over n expansion. So you take this function, you consider a 1 over n expansion, or an expansion in inverse powers of the central charge, and the first is a disconnected contribution, and the second piece, this non-trivial piece, is what would match to a 3-level amplitude on the string theory side, is this non-trivial contribution. Now, this is still very complicated, and we don't know this function, so something that we could do is to compute this in a further 1 over lambda expansion. So for instance, if lambda is very large, we get what we call the supergravity contribution, and the supergravity contribution was computed more than 20 years ago, but we are interested in this whole tower of 1 over lambda contributions. And it is this whole tower, I will be a bit more precise in a bit, but it's this whole tower, the whole lambda dependence that we are after. And this whole dependence is what we would call the Virasoro-Shapiro amplitude on ADS. Is that okay? So, we want to consider the scattering of 4 gravitons in ADS. Juan Maldacena tells us that to do that, you need to compute the correlator of 4 stress tensors in n equals 4 super Yang-Mills. Because we are only interested in the 3-level amplitude, we expand in 1 over n and keep the first non-trivial term. Is that okay? That's what we are doing. That's all. Beautiful. Now, the best formulation to do that is a formulation where the correlator looks much more like an amplitude. So far, I started talking about an amplitude in flat space, functions of 3 Mandelstam variables, and now we are talking about a correlator. They look quite different, but there is a formulation, which is Meline space, where the two things actually look very much the same. And from this correlator, that is the one that we are going to consider, we define the Meline amplitude by the following transform. So this is very similar to a Fourier transform, where this is a prefactor with some GAN functions, and this one here is what you would call the Virasoro-Shapiro amplitude in ADS 5 crosses 5. And this object here is a meromorphic function with very nice properties, which are the properties from which we would try to guess this function here. Is that okay? Now, of course, knowing these to all orders in 1 over lambda would be equivalent to knowing this, and we don't know this, but we know the list of properties it satisfies. Okay? So the list of properties is the following. So first, this object here is crossing symmetric. Then exchange operators lead to simple poles. Now, this seems very similar to the poles that you had for the Virasoro-Shapiro amplitude, it is quite different and much harder. First, notice that there is an infinite sum over M, and this is because in a conformal field theory, once you exchange an operator, you exchange all the descendants of the operator as well. And the second point is that these polynomials are much more complicated than the polynomials we have in flat space, because they are called what we call Mach polynomials. And we don't even know a closed form expansion for them, a closed form expression. But just for a talk, this looks very similar to the previous one. But I am just telling you it's much harder. Then it also has some Regge limit. And finally, we know that, imagine that you have ADS 5 cross S5, and we scatter 4 gravitons, and the scatter of 4 gravitons happens in the tip of my fingers, right? And I make the radius of ADS and S5 huge. These 4 fingers wouldn't care whether they are in flat space or in ADS, right? So there is a limit, a large radius limit, where a flat space limit, where this amplitude should reduce to the usual Virasoro-Shapiro amplitude. Is that okay? And now the game is to try to guess these amplitudes from the list of properties. Now, the upshot will be that we are not as smart as Virasoro, we knew that, but at least it seems to be that if you add one more constraint, then this list of constraints is pretty powerful. Okay? Any questions? Yes?
I think I maybe even asked you, shouldn't there be some alpha prime hiding in Regge?
Yeah, I mean, I will be incredibly precise on that, because I will write a formula for it. Yes, but you are right, but people in CFT proves different things, and this is the kind of results that have been proven in CFT, but I can be much more precise than I was the last time you asked me this question. Yeah. Let's put it like that. Yeah. But I just wanted to be completely honest, and this is the result that people has proven in a CFT. They have proven that the Mellin amplitude is smaller than this in this regime. But what happens is that there is an alpha prime, but that like kind of multiplies S. So in this regime, this is true. Yeah. So I guess that's the answer. Good. So let's try to get some intuition. This, I feel, is a bit abstract because I am putting you names and I am not telling you what these functions are, because we don't know what they are, but we know a little bit. So we can consider this Mellin amplitude, or this ADS Virasoro-Shapiro amplitude, in a 1 over lambda expansion. The leading order result, when lambda is infinity, was gotten 22 years ago. In a space-time was a very complicated expression, but in Mellin space, it looks super nice, and it's just this. And then, in addition, we have 1 over lambda corrections, right, that look very similar to these polynomial corrections that we got in flat space, but the difference is that the polynomials here are not homogeneous polynomials. So in the case of flat space, we always got a homogeneous polynomial of degree 0, degree 2, degree 3. Here, we also get all the lower order terms, okay? And that makes this much more complicated. And all these coefficients, we don't know them. These are the coefficients that we would like to find out. Now, the flat space limit, as I mentioned before, is a limit where you take the radius very large, and remember that taking the radius large is the same as taking this lambda large, but then you need to rescale these Mellin variables, st and u, appropriately, okay? And you rescale them in such a way that in the flat space limit, only the leading pieces at each order survives. So here, 1 over stu survives, Here, well, 1 survives. Here, only this quadratic term survives. Here, only the cube survives, etc. Okay? And what we know, or what we expect, is that these should precisely agree with the flat space answer, which is the usual Virasoro-Shapiro amplitude. Okay? More generally, we can now rewrite this ADS amplitude in a different expansion, where we write it as the Virasoro-Shapiro amplitude in flat space, plus a series of curvature corrections. Okay? So we write this expression in a 1/r expansion. Okay? So we are kind of reshuffling this expansion in such a way that we put all the leading terms in what we call the Virasoro-Shapiro, all the subleading terms in A1, all the sub-subleading in A2, and so on. So in this way, we can interpret the first term is just the Virasoro-Shapiro amplitude in flat space, and the second, the third, etc., are the 1/r square curvature corrections that arise because the background is curved, is not flat. Okay? So this is a very natural expansion. Beautiful. So now I can tell you what our assumption is. Notice that if we do this, we get that M3 is a sum of the Virasoro-Shapiro amplitude in flat space, plus the first curvature correction, plus the second curvature correction, and each one of these also admit a low energy expansion, a small alpha prime expansion. The coefficients here for the A0 are the coefficients that we have already learned about, are just the Virasoro-Shapiro amplitude in flat space. And these coefficients are unknown coefficients. I don't know what alpha 1 is, I don't know what alpha 2 is, etc. Okay? And now comes the assumption. We are going to assume that these unknown coefficients, and the unknown coefficients of A2, etc., whatever they are single-valued zetas. Okay? We have no proof whatsoever of this. We will take it as our working assumption. We will try to understand how powerful this is, and then we will try to see whether we can check our conjectures. Is that okay? So, we don't have a worksheet theory. The story of this is quite funny. So I was in a pub with Michael Green, and I think in an older version of one of our papers, alpha 2 was not single-valued, and then Michael Green told me, I think that's wrong, and I asked him why, and he told me because it's not single-valued, and then I asked, what's this thing of single-valued? I had no idea what it was. And then I started studying it, and I started talking to Tobias, and we worked out the the implications of these coefficients being single-valued. And as you will see, they are quite powerful. Okay? Good. So this is our assumption. So now, the full list of conditions are the same as the conditions 1 to 4, the same 4 conditions we had before, but in addition, the low energy expansion of M3 contains only single-valued zetas. Okay? Very nice. So now, I have to tell you one more thing, and then I will give you the final result for our proposal, and we will see what are the conclusions of that. It turns out that this structure, so somewhere hidden here, is the structure of poles of different things in the 1/radius expansion. Remember that we saw that the Virasoro-Shapiro amplitude has single-order poles here, right? Single-order poles. It turns out that the pole structure of the curvature corrections is a bit more complicated than that. And in particular, A1 has 4th-order poles, okay? So this is usually quite common in quantum field theory. So in a quantum field theory even, an S matrix has single order poles, but then if you expand in a small parameter, a single order pole can become a higher order pole, okay? So this structure, actually, the fact that A1 has a fourth order pole, follows from the EDS propagator if you take an EDS ball-to-ball propagator and you expand it around flat space. You will see that the first correction to that has a fourth order pole, the other correction has a seventh order pole, and so on. And it turns out that this structure make us propose the following ansatz. And here comes the ansatz. Remember that Green, Schwarz, and Witten told us that A0 has an integral representation, which is an integral representation like this, okay? So it's an integral over the complex plane. What we want to do now, we want to say that A1 has a very similar integral representation, but we add something extra, okay? And we want to know what this extra thing is. And notice the following. Imagine that I tell you, can people see if I write here? Yeah? So imagine that I tell you that we have 1 over S minus N, and I want to take derivatives with respect to S in such a way that I increase the order of the pole, okay? If we take one derivative, we end up with a second order pole. If we take two derivatives, we have a third order pole, and if we take three derivatives, then we end up with a fourth order pole, right? So a very cheeky way, a very easy way to obtain a fourth order pole would be taking this expression and taking three derivatives with respect to S, okay? But taking three derivatives with respect to S, you just act on the integrand, and you will see that this inserts log of z bar cube. Okay? Very simple. So you take three derivatives with respect to S, and this is equivalent in this to insert this function. But we have seen this function. This function, exactly that, is a single-valued function. Of transcendentality 3. So what we are going to say now is that whatever it is, the first correction to the Virasoro-Shapiro amplitude is the same integral representation as the Virasoro-Shapiro amplitude with the insertion of single-valued polylogs of weight 3. And this is very cool because it means there are mathematical results by Van Hoff, actually, and Cervini, that tell us that when you expand this at a small alpha prime, you will automatically get the single-value zetas that we were after. Okay? If you do the same trick, then what you would like to say is that A2 is the same, but you insert single-valued polylogs of weight 6. Okay, there are other ways to see this, but this is a very nice way to see that this is what we get. But now we are on fire, okay? Because first, I told you that we had like an infinite number of coefficients to guess, right? But now we don't anymore, because we are telling you this, and there is only 8 single-valued polylogs of weight 3, okay? So now the ansatz has reduced from an infinite number of poles, of coefficients, to kind of 8 coefficients, basically. So it turns out, okay, so this, I don't know if I have like a few minutes, but yeah, maybe I will go ahead. But basically what happens, one can put a basis of polylogs of these single-valued polylogs of weight 3. There is only 8 of them. They are labeled by 3 numbers, A, B, and C, which can be either 0 or 1. For instance, this is log cube, and this is Li3. They are a bit more complicated, but there is basically 8 of them, and we just add zeta 3. Why not? It's like adding some salt at the end of a recipe. So, and okay, there is some very simple dependence on S and T, but the point is that the number of unknowns is very small. And it is so small that the structure of poles is so constraining that this answer is fixed uniquely. One can even go farther, especially with the help of Tobias, which is extremely good at these things. And you can go to W6, you have something like 140 functions, but again, the whole structure is so constraining that we needed one extra result, let's say from localization, to fully fix the answer. So the status now is that we have an expansion like this, and the expression is crossing symmetric, is single-valued for low energy, and the structure of poles is so constraining that the answer can be fixed just by one more input, for instance, by localization results. Now, how do we know that this has to do with n equals 4 at all? Now we can do something quite smart. We can have a look at the answer we have gotten, and we can have a look at which intermediate operators it has. And from the answer we got, without putting this as an input whatsoever, we see that there is an intermediate operator whose 1 over lambda expansion is exactly this expansion. And we go to integrability people, and they tell us that is exactly the dimension of the Konishi operator in a 1 over lambda expansion. And this is true not only for Konishi, it is true for all operators like Konishi-like operators. So from this answer, we produce a wealth of CFT data, and we agree with every single known result of integrability just for free, you know. We just ask for single valuedness, and basically this follows, which makes us confident that the answer is correct. Now, if I have 2 more minutes, I would like to mention something, and with this I will be done. Or I can take a question maybe now. Is there any question?
Do you think you can resolve that series? It's a series in alpha prime.
Oh, that would be
an expansion of something.
Beautiful. Let me do that. Yeah. So of course, Costa's question is an amazing question. And can we guess the result to all orders in 1 over R? Okay. And yes, but only in particular regimes. Notice, by the way, that this Virasoro-Shapiro amplitude, in particular, should encode and encapsulate all the results of integrability for planar n equals 4 super Yang-Mills over the last 30 years, okay? Once you have this beast, you could look at the poles, and from the poles of this beast, you read all the dimensions of intermediate operators. And from the residue, you can read all the OP coefficients. So the answer we are expecting could be extremely complicated answer. But still, we would like to guess these to all orders in 1 over R, or even better for finite R, but that would be even harder. And actually, there are 2 particular regimes where this can be done. One regime is the high energy limit, where S and T are very large, and the other is richer, where T is much bigger than 1, but S is finite. And in the high energy limit, this was analyzed by Gross and Mende in their classic papers, and it turns out that the whole worksheet integral localizes to this point Z bar equals S over S plus T. And it turns out that, as we saw in this paper, in ADS, 1 over R corrections exponentiate in this limit. So in the high energy limit, we get a formula which is valid to all orders in 1 over R, but in each order, you keep only the large ST leading contribution. And in that limit, we get this beautiful exponential. There is, and this is the last slide before the conclusions, there is another regime which is which is richer, actually, which is the Regge limit. In the Regge limit, we take T very large, but S is not large, is finite. And as we know from Regge theory, this limit, we keep full information on the leading twist operators. For instance, these Konishi-like operators. And what we find is that in the Regge limit, we can obtain a formula to all orders in 1 over R, where this formula is this differential operator acting on the Regge limit of the usual flat space Virasoro-Shapiro amplitude. So it's the usual T to the alpha prime S minus 2, whatever. And this operator here basically encodes the curvature of a space-time, and it has an expansion in 1 over R like this. It's some kind of complicated operator. You can see that it's 1 plus degree 3, degree 6, but it satisfies a differential relation that can be solved to any order in 1 over R. So in the Regge limit, we don't have explicit formula, but we have a formula to any desired order in 1 over R in terms of this recursion, in terms of these relations. And this answers fully your question. This is the Regge limit of the Virasoro-Shapiro amplitude in ADS. So let me finish here. So computing the full ADS Virasoro-Shapiro amplitude now seems within reach, and it seems that single valuedness plays a very important role in ADS as well, and this offers connections between standard bootstrap techniques, localization, integrability, and number theory, and there are these two regimes, which are the high energy and the Regge regimes, that provide a much more manageable limits. And there has been similar developments for open strings, as discussed by Tobias in his talk. And I think the best question now for the near future, I wrote a few questions, but I think the best one is that in string perturbation theory, we don't yet know how to compute scattering amplitudes in the presence of Ramon-Ramon background. And now, for a very simple example, simple but at the same time highly non-trivial, we have an answer. So now it would be great to try to start from string theory and try to come up with the first principles derivation of this result. Thank you very much.
Okay. So do we have any further questions?
Yeah, maybe I can follow up on the point you just made. Pure spinners, of course,
Yeah.
we can write string theory on ADS 5 crosses 5 with pure spinners.
Yes.
Do you think it's possible?
Yes, actually, that if I have 2 minutes, because I have been discussing this with postdocs of Nathan Berkowitz. So there are like a few steps that you will need to do with the pure spinner computation. I think it is extremely promising. And the first step, so they work out the vertex operators for half BPS states with some choice of R charges. So first, technically, one needs to generalize this to arbitrary R charge. And I think they are now at the point where, in principle, in the very near future, they could compute 3-point functions of this. That, as you know very well, it has, they are protected, OP coefficients. So I think that would be the two computations that I could imagine in pure spinor. The next frontier is the 3-point function of 3 BPS operators that doesn't depend on alpha prime, and the dimension of Konishi operator. That is what they want to get now. And I think then the next step would be this, and that would be beautiful. And I also heard from Yin that in principle, in string field theory, they already have all the ingredients to compute this in a 1/r expansion, exactly as we do. One of the people working on that left the field, so that is a backslash, but in principle, they do have all the ingredients. So in string field theory, one should also be able to do this. And yeah, it would be amazing. Yeah, in any of the two. It was, I think it was. Yeah.
When you say localization there, like where did integrated correlators or
Absolutely, absolutely. So
Where did
sorry,
it-
I didn't explain that very much. So the idea is that if you take n equals 4 and you give it a mass deformation, you can use localization techniques to compute an integrated version of the same correlator I was computing. And basically what this gives you is a linear relation, is linear relations between these coefficients here. And the linear relations are very powerful to low orders in 1/λ. At higher orders in 1/λ, they become less and less powerful because we have many terms here. But they add extra constraints. So what we have now is that either you use localization and then you can check, for instance, that the dimension of Konishi is what I wrote before, or you could, let's say, use these two and check localization from our results. So there is some, yeah, there are some non-trivial checks, but we need at least one of them at that order.
So yeah, a question about the Regge limit that you were mentioning.
Yes.
Right. So in flat space, when you take the Regge limit, the amplitude develops. The three-level amplitude develops also an imaginary part.
Yes,
Right.
we have the same here.
You have the same here.
Absolutely.
And
absolutely.
then, can you see the correction of the Regge slope?
Yes, you can actually. You can. So, but yes, very much. So actually, what you, I mean, there are two ways. So this formula here. So we have a formula, and this formula depends on the CFT data of the operators in the leading Regge trajectory. So something that you could do, and we did that, is we took the results that we found with Tobias, and from these results, you compute the Regge limit, and then you can read off indeed that the Regge trajectory bends. Or you could do the opposite, and you could plug the CFT data, and you could compute the same. But indeed, you see, so basically, this goes like T to this J star, where this J star is the Regge pole. So is the value, so is S, sorry, I am a bit technical here, but basically it is the solution to this equation, where this is the dimension of the operators in the leading Regge trajectory as a function of the spin. So this, indeed, we see this. So we see precisely what we are expecting. And indeed, it has an imaginary part, but all the imaginary part arises from here. This operator is a real operator. So it's a real operator, so that the imaginary part is already determined by the imaginary part of the flat space. We don't get anything new. So, yeah.
Thank you for the wonderful story, Fernando. Do you see any hope to push it to genus 1?
Oh, no. But however...
There are analogs of...
No, I have an
genus
idea
1.
that would be amazing, actually. So the first thing, according to, which I already find fascinating, is, some mathematicians love this sort of stuff, is that the first question is whether one can define, because when you are in genus 1, the integrals are not integrals over the complex plane anymore. They are integrals over the fundamental domain of the torus. So the question number 1 is whether you can define single-valued functions that are functions of this fundamental domain on the torus, right? Because here set and set bar are complex, are just a complex plane. And you can. Actually, mathematicians have extended this construction to these functions. So the claim would be that if you take the genus 1 string amplitude of strings on flat space and you add these functions, then you will get genus 1 in ADS. But these are very hard integrals. But in principle, that would be the idea. Yeah. So I think maybe in a few years. Yeah, it's a beautiful question, I find.
All right. Well, that was great. So we'd like to thank
Thank you.
for
Thank you. Thank you.